So, in the previous session, we have discussed about, say, uh, conversion of temperature from one scale to another scale, and then we have discussed about calorimetry, the concept of specific heat, the concept of latent heat of melting, latent heat of vaporization, and all. Okay. So, Uh, so we had done a numerical on when you are mixing a ice with water, how the temperature rises, like how the ice melts into water faster, and then the temperature rise of water happens, and what will be the resulting temperature and all. Okay. Then we have discussed about specific heat and we have discussed about the thermal expansion also. Okay. So linear linear coefficient of thermal expansion, area expansion, volume expansion, and all that. Okay. So now we'll discuss about. So the remaining thing is our heat transfer. Okay. Heat transfer is very important concept. Okay, we must. There are so many things that is happening in nature, which can be solved using the principle of heat transfer. Okay, for example, you want to find a temperature distribution. Suppose you are hitting a iron rod from one end. Okay, you are hitting an iron rod from one end and you want to find out the temperature distribution throughout the length of the rod. Okay. So that so uh, and yeah, so to find out the temperature distribution, it is necessary to find out the temperature distribution. So using some principle of heat transfer, you can find out. Okay. So basically, broadly, there are three modes of heat transfer. Okay. Um, So one is conduction, one is convection, and one is radiation. Okay. So conduction is this is your conduction. Okay. So so the transfer of heat from one part of the body to other part of the body is called conduction. Okay. So let us say you have a iron rod. Okay. So this iron rod you are hitting by this candle is a heat source. So you are initially, let us say the rod is at room temperature 20 degrees centigrade. But after you supply some heat, let us say the temperature of one end of the rod has it is raised to 100. Okay. So if it is raised to 100, there can be question what is the temperature of the rod at different location. So you can just intuitively you can say that it will become 100, then 90, then 80, then 70, and this 20 may become 25 or 30. So near the heat source the temperature will be more, away from the heat source the temperature will be less. Okay. So that is conduction, where the heat is transferred from one part of the body to other part. Okay. And there is convection. Okay. Convection, there are two types of convection. One is natural convection, another is forced convection. So natural convection, let us say we have a vessel and we have some water in it. Okay. So we have some water. Okay. So then again I am heating this vessel using some fire or whatever. So what will happen? The density of water which is near at the bottom, it will decrease. So if the density decreases, uh, uh, then the lighter one will go up and the heavier one will come down. Okay. So there will be a kind of a circulation here. So the lighter one will try to go up. Okay. And the heavier one will try to come down, and again once it comes down, again it will get heated up and again it will go up, right? So this kind of like mixing and the transfer of heat, this is called natural convection. Okay, this is natural convection. So this is called natural convection. Okay. and there is something called a forced convection. Suppose you have a like you have a pipe, okay, and let us say kind of let us say you have a pump, okay. So the pump it will be discharging some liquid, okay. So the pump will be discharging some pressurized liquid, okay. So you have a pump here. So the pump is discharging some pressurized liquid, and let us say you have the pipe, okay. So you have the pipe. So through this the pressurized liquid is flowing, okay. So let us say this is a hot liquid, okay. So the transfer of heat from this hot liquid to the atmosphere. So that phenomena, like suppose you want to see that you have a very hot pipe is there. So how what will be the temperature of the surrounding, or how much heat is getting transferred from this fluid to the outside, okay. So that is called like the forced convection. Why it is forced? Because this liquid is being forced by this pump. Okay, so that's why it is called forced convection. Forced convection. Forced convection. Okay. So another example of forced convection is your circulatory system of human body. Okay. So our heart is also a pump. Okay. So our heart is also a pump. So our heart is sending pressurized blood. Okay. Uh, our heart is sending pressurized blood to different parts of our body. So let us say this is my heart, and let us say this is my pressurized blood. It is going to different parts of the human body. Okay. So this method, this flow of blood to different parts of body being pressurized by heart is also an example of forced convection. Okay. So we have discussed what is conduction and what is convection. So in both these cases, you need a medium for transfer of heat. Okay. So here it is transferring from one part of the body to another part of the body. Here also in convection you need a medium, like here the through the water, or here
Pipe.
from this hot water it is getting transferred to the outside surrounding through this pipe or whatever. So you need a medium for transfer of heat. Whereas in radiation, you don't need the medium. Okay. So through vacuum can heat can also be transferred. Okay. So this is that is radiation. So the example is the transfer of heat
From the
from
sun.
sun to the earth surface. Okay. So the example of radiation is transfer of heat from sun to earth surface. Okay, so the main important thing is that no need of medium. Need of medium. And this uh, thermal wave are nothing but electromagnetic waves. Electromagnetic wave does not need medium, right? So that those are radiation. Okay. So you can take a picture of this. So these are the three basically. So we'll get into the mathematical formula related to this, using which you can solve the numericals. Okay. So you took the picture.
Yeah.
Okay. So the numerical related to conduction. Okay. There is a conduction. Now what is the governing formula? So yeah. So let us say I have a iron rod. Okay. So let us say my temperature at one end is T1. It is absolute temperature. and my temperature at other end is T2. Okay, so that is the temperature. Okay, and let us say the length of this iron rod is, this is a conductor, iron rod is a conductor, length is, let us say, L. Okay, so and the cross sectional area, so if you take the cross section of this iron rod, it will be something, some circular things like this. Okay, so if it is circular, say A is equal to pi by 4 d square or whatever, that you can find out if you know the diameter. Okay, so the amount of heat transferred in this kind of situation is H, or you can write it as K also. So amount of heat transferred, which is equal to Q, is equal to Ka T1 minus T2 divided by L. Okay, so this is heat transferred. Okay, now so this is actually this is a rate of flow of heat. Okay,
by L. That's why.
So this is Q dot is, it is Q dot actually,
Rate.
not Q. Dot means rate. Okay, per unit time. Okay, so Q dot is equal to Ka delta T, we can write, divided by length. Okay, so the unit of Q dot is equal to, you can say it can be joule per second, right? Because I am saying flow rate. Okay, or it can be kind of say calorie per second or whatever. That is the unit Q dot. Okay, so and so this term, important term comes here, is your K is called thermal conductivity of the material. Thermal conductivity of the material. Now, this is a property of any material. It is a property. Okay, so so we can say that iron is a very good conductor of heat, very good heat conductor. So that's why its conductivity will be high. Okay, but if you have a wooden rod, okay, so conductivity is much less. Okay, so there can be questions, what is the unit of conductivity? Okay, how will find the unit? So Q dot is equal to Ka delta T by L. Okay, so K is equal to Q dot divided by A, numerator L, divided by delta T. Okay, so your Q dot is equal to your joule per second. Then L and A, if they cancel out, it will just become your meter, and delta T is your Kelvin. Okay, so this is joule per second, joule per meter Kelvin, or you can, joule per second is nothing but your watt, right? Watt meter Kelvin, right? So that is your unit of thermal conductivity. There can be questions, is what is the unit of thermal conductivity, which is watt per meter Kelvin. Okay, and clear? So you just remember this the equation. Okay, Q dot is equal to Ka delta T by L. So it is not Q. There can be confusion. So it is heat flow rate. So what does it say? How do you interpret it? Like heat flow rate is directly proportional to cross sectional area. Right? Q dot is directly proportional to cross sectional area.
Inversely proportional.
Directly proportional to temperature difference. Inversely proportional to length. Okay. So what does it mean? That means if I have a rod and I am heating it, okay, so because it is inversely proportional to L, that's why, like as the length increases,
Conduction
the temperature will be less at a far off place, right? So and similarly, if the cross sectional area increases, suppose instead of this, if I increase the cross sectional area to something like this, if I increase the cross sectional area, then also the heat transfer will be more. So it is directly proportional to area, inversely proportional to length. Similarly, it is directly proportional to temperature difference.
Yeah.
If the temperature difference is
1.1.
very high, there will be more heat transfer. Okay, that's the interpretation of this conduction equation. Okay. So take a picture of this. We'll cover some more concepts. Okay. So um, this is about the conduction. Okay. So there are some other things related to this. One is your Wein's displacement law. Okay. That is Wein's displacement law is related to radiation actually. Okay. Black body radiation. Okay. So we will just touch upon what is Wein's displacement law. Okay. So Wein's displacement law. Okay. So in the if I draw a curve, okay. So I have a x-axis, I have a y-axis. So in the x-axis you have lambda, which is nothing but your wavelength. Okay. So it is wavelength of radiation, right? Wavelength of thermal radiation, right? And in the y-axis you have radiation energy per unit area per unit wavelength. So in the y-axis you are just your radiation energy per unit area per unit wavelength. Unit wavelength. So basically it is energy density, you can see. Per area means energy density in the y-axis. Okay. So when you draw this for different temperature, you can find out there will be different curves. Okay. So this is something like this. Okay, this is one. Okay. So this is your let us say this is your these curves are at constant temperature. Okay. So this is kind of a lamp filament. Okay. Lamp. Okay.
Red color.
Lamp filament. Filament. So you can see your electric bulb. So it may be at let us say it is at 2000 Kelvin, right? So the temperature. So this curve is for a constant temperature, which is 2000 Kelvin. Right? So this is the radiation from a electric bulb whose temperature tungsten filament is of 2000 Kelvin. Okay, then if you go to the welding arc, you might have seen welding happening. They will have a welding machine. There will be arc and all. So for welding arc, there will be another curve. Okay, so there will be another curve. Let us say this curve is something like this. Okay. So there will be another curve. So this is welding arc. Welding arc. The temperature of welding is around 3000 Kelvin. 3000 Kelvin. Okay. So then beyond that, let us say this is sunlight. Let us say this is sunlight.
Highest temperature.
The highest. And the temperature of sun is 6000 Kelvin. Okay. Sunlight. And it is 6000 Kelvin. So we can imagine like 5723 degrees centigrade, such high temperature. It is a surface of sun. Okay. So the observation from this is like with increase in temperature, the wavelength at which the energy density is maximum is decreasing. Right?
Understood.
So you have a wavelength here. Okay. So you have a wavelength here. Okay. And you have kind of a wavelength here. Okay. So you can see like let us say this is my lambda 1, this is my lambda 2, this is my lambda 3. So with increase in temperature, like when it is increasing the temperature, so this is lambda 3 is less than lambda 2 is less than lambda 1, and like say temperatures, like say this is 3, so T3 is this is lambda 3, T3 is greater than T2 is greater than T1. So there is a inverse relation, right? There is a inverse relation.
Between wavelength and temperature.
So based on this observation, the scientist based on the scientist Wein, this is called Wein's displacement law. Okay, so Wein's displacement law. Displacement law. So the equation for Wein's displacement law is lambda m. So this you can see write as lambda m because this is maximum wavelength.
Yeah.
So we write it as lambda m2, lambda m1. Okay. So the lambda m into capital T is equal to constant. Okay. So this is Wein's displacement law.
Yeah.
Okay. So now to find out the temperature, knowing the wavelength, you should know what is the Wein's constant. Okay. So this term constant will be given. It is a constant. Okay. Then the value of the constant you just have to remember. It is Wein's constant. Constant is equal to 2.9 into 10 to the power minus 3. 2.9 into 10 to the power minus 3 meter Kelvin.
Yeah.
So just remember the unit of Wein's constant is meter Kelvin because you are multiplying wavelength which is meter. Unit is meter and T is Kelvin. So meter Kelvin. So this is the value of your Wein's constant.
Yeah.
Okay. So you can take a picture and then we will try to explain the utility of Wein's law. Okay. So the utility of Wein's law. So where do we use it? Okay. So Wein's law is useful to estimate the surface temperature of celestial bodies like moon, sun, and other stars. Okay. So to find out the surface temperature of celestial bodies like sun, moon, and stars. That is the utility. So how do they find out? Like say, let us say I want to find out the temperature of moon. Okay. So how to surface? So find one numerical